Where did all the stuff in our universe come from? Think about it. Every star, every planet, every living thing. All of it is made of matter and energy. It seems to break a fundamental rule we learn as children. You can't get something from nothing. This question sits at the very heart of cosmology. It presents a profound paradox that challenges our everyday intuition. We look out at a cosmos filled with the brilliant light of a trillion galaxies. And we are forced to ask, was all this energy and matter borrowed, or was it created? If so, how? The sheer scale of the universe's energy content feels like it must have had an epic source. This cosmic riddle leads us directly to the Big Bang. But our common picture of the Big Bang is often a bit misleading. We imagine a colossal explosion happening at a specific point in an empty, pre-existing space. But that's not what the science tells us. The Big Bang wasn't an explosion in space. It was the beginning of space, and time too. So, when we ask the question, what happened before the Big Bang? We are making a logical error. The very concept of before depends on time. If time itself began with the universe, the question becomes meaningless. It's like asking what's north of the North Pole. The problem, then, isn't about finding a power source that existed prior to our cosmos. The real mystery is understanding how a universe could come into being without violating the laws of physics as we know them. Specifically, the law of conservation of energy. This law states that energy cannot be created or destroyed, only changed from one form to another. If the universe started with zero energy, and now it's filled with an immense amount of it, how do we reconcile this apparent contradiction? The answer requires us to rethink what nothing truly is and to explore the deepest, most counterintuitive aspects of reality. What if the total energy of the universe is, and always has been, exactly zero? This isn't just a clever accounting trick. It's an idea rooted in the fundamental properties of matter and gravity. It suggests that for every bit of positive energy that exists in the form of stars, in the form of galaxies, in the form of radiation, there is an equal and opposite amount of negative energy. The universe, in this view, is the ultimate balanced equation. It's a grand cosmic loan that costs nothing to take out because its positive and negative assets perfectly cancel each other out. This concept of a zero-energy universe is our first major clue to solving the paradox. The idea of a zero-energy universe sounds strange at first. How can anything be negative energy? Let's start with what we know as positive energy. This is the energy of things, energy locked inside matter. Einstein's famous equation, E=mc squared. The kinetic energy of a planet orbiting its star. The radiant energy of light traveling across space. When we add up all the matter, we get a fantastically large positive number. This is the side of the cosmic ledger we can see and measure. It's the something we perceive around us. Now the other side, negative energy. Its source is gravity. Imagine lifting a book off the floor. You must expend energy to pull it away from Earth's gravity. Because you put energy in to separate the book and Earth, the gravitational field itself stores negative energy. The stronger the gravitational pull, the more negative the energy. All massive objects are pulling on each other. Stars, black holes, galaxies. That cosmic web of attraction is an enormous debt of negative energy. The zero-energy hypothesis says these two quantities balance perfectly. The immense positive energy of matter and light is exactly canceled by the immense negative energy of gravity. Think of digging a hole. You create a pile of dirt, like positive energy. The dirt can fill the hole, leaving flat ground again. In this analogy, the universe is the flat ground. It looks like something, but the net change is zero. That has a powerful implication. If total energy is zero, conservation of energy wasn't violated at creation. The universe could have started from zero energy without external input. It didn't need to borrow energy from elsewhere. This turns the Big Bang from magical to a natural process. It could have occurred spontaneously, governed by physics, without requiring a traditional first cause. The universe could be the ultimate free lunch. So if the universe could appear from nothing without breaking energy laws, what was the trigger? What mechanism could kickstart a cosmos from a state of zero? The answer may lie in the strange and wonderful world of quantum mechanics. On the smallest scales of reality, the universe is a jittery, uncertain place. It is a seething cauldron of activity. Pairs of virtual particles, antiparticles popping into existence, annihilating a fraction of a second later. This is called a quantum fluctuation. These fleeting events are possible because of a core principle of quantum physics known as the Heisenberg uncertainty principle. You can never know both a particle's position and its momentum with perfect accuracy at the same time. A related version applies to energy and to time. It allows tiny amounts of energy to be borrowed from the vacuum, provided they're paid back quickly. The more energy borrowed, the faster it must be returned. This is the cosmic loophole that allows something to briefly emerge from nothing. Now, imagine taking this idea to its ultimate conclusion. But very rarely one could be much larger. Some physicists, like Alan Guth, have proposed our universe began as one such fluctuation. A minuscule patch of primordial vacuum, with its own nascent laws, fluctuated into existence. Instead of disappearing, something extraordinary happened. That tiny seed underwent a period of hyper-fast expansion, cosmic inflation. Inflation stretched a subatomic speck to astronomical proportions in seconds. The rapid expansion flattened out space-time and magnified the fluctuation's initial energy into the vast, hot, dense, early Big Bang. Crucially, the total energy of this new universe was zero. Gravity's negative energy balanced matter's positive energy, so the process could happen spontaneously. The nothing here was a quantum vacuum, a state of potential governed by physical laws that permit such a creation. Section 4. The primordial furnace, density, and cosmic heat. One of the most defining features of the early universe was its incredible heat. Immediately after the Big Bang, the cosmos was a blazing inferno, hotter than the core of any star today. But where did this heat come from? It wasn't injected by some external furnace. The heat was a direct consequence of the universe's own properties. It came from cramming an immense amount of energy into an unimaginably small volume. It's the same principle that makes a bicycle pump get hot when you compress air into a tire. Squeezing energy into a smaller space makes it hotter and more intense. In the first moments after its birth, the universe was incredibly dense. All the energy that would eventually form every galaxy, all the energy that would eventually form every star, all the energy that would eventually form every planet was concentrated in a region smaller than an atom. This energy existed as a plasma of fundamental particles, high-energy radiation, all colliding at near the speed of light. The temperature was astronomical, trillions upon trillions of degrees. This wasn't heat added to the universe. It was the inherent state of the universe's energy when confined to such an extreme density. The Big Bang was not just the beginning of space and time, but also the beginning of this primordial heat. As the universe began its expansion driven by the initial inflationary push, the space itself stretched. This stretching had a cooling effect. The energy that was once packed together became more spread out. The wavelengths of light were stretched, causing them to lose energy and cool down, a process known as cosmological redshift. Over thousands of years, the universe cooled enough for protons and electrons to combine and form the first atoms, primarily hydrogen-helium. At this point, the universe became transparent, releasing the light that we now observe as the cosmic microwave background radiation, the faint afterglow of the Big Bang's fire. A universe that remained eternally hot would have been a universe where no structures could form. There would be no stable atoms, no stars, no planets, and certainly no life. The expansion of the universe and the subsequent dilution of its initial energy density is what allowed the cosmos to evolve. The initial heat wasn't a separate ingredient, but a natural result of the universe's birth conditions. The journey from a hot, dense state to the cool, structured cosmos we see today is the grand story of cosmic evolution. Section 5. Gravity's debt, the negative energy of space-time. We need to look at gravity through the lens of Albert Einstein's general theory of relativity. Einstein revolutionized our understanding of gravity. He showed it's not a force pulling objects together in a static space. Instead, gravity is a consequence of mass and energy warping the very fabric of space-time. Imagine a bowling ball on a trampoline. It creates a dip, and marbles rolled nearby will curve toward it. This is a simple analogy for how planets orbit stars. They are following the straightest possible path through the curved space-time created by the star's mass. This connection between energy and the geometry of space-time is key. In general relativity, the energy of a system is more complicated than in classical physics. The total energy includes not just the energy of matter and radiation, positive, but also the energy stored in the gravitational field itself, negative. As the universe expands, the energy of matter and radiation decreases. You might think this violates energy conservation, but general relativity shows that the energy lost by matter is gained by the gravitational field, which becomes less negative. The total energy remains constant, and in a flat universe like ours appears to be, that constant is zero. This concept of gravitational energy as a negative debt is fundamental. Every time a star forms or a galaxy forms, its gravitational field becomes stronger, and the negative energy associated with it increases. This creation of structure is paid for by the accumulating gravitational debt. In a sense, gravity provides the funding for the formation of the universe's contents. By the negative energy of the gravitational well it creates. This cosmic accounting ensures that the universe's books are always balanced, even as it evolves and becomes more complex. This relativistic view provides a robust mathematical framework for the idea of a zero-energy universe. It's not just a philosophical concept, it's a consequence of our best theory of gravity. It means that the universe could have started with a total energy of zero and then evolved, with matter and energy appearing as space-time expanded and gravity provided the necessary negative balance. Einstein's theory not only describes how the universe works now, but also provides a plausible mechanism for how it could have come into being from a state that, in total, amounts to nothing. We all experience time as a one-way street. The past is fixed, the future is open. We move steadily from one to the other. Physicists call this the arrow of time. But why does time have a direction? The fundamental laws of physics, for the most part, don't care about the direction of time. A video of planets orbiting a star would look just as physically plausible if you played it backward. The answer to this mystery lies not in the laws themselves, but in the starting conditions of our universe. The arrow of time is a consequence of the universe starting in a very special, highly ordered state. This concept of order and disorder is captured by a physical quantity called entropy. The second law of thermodynamics, one of the most fundamental principles in all of science, states that the total entropy of an isolated system can only increase or stay the same over time. It never decreases. A broken egg will never spontaneously reassemble itself. A cold cup of coffee will not suddenly become hot on its own. These are examples of entropy increasing. Disorder. Randomness tend to grow. Our universe is no exception. It is constantly moving toward a state of higher entropy. The reason we have an arrow of time is that the universe began in a state of incredibly low entropy. The smooth, hot, uniform plasma of the early Big Bang was a highly ordered state. It was like having all the air molecules in a room packed neatly into one corner. From this special starting point, the universe has been expanding, cooling, and evolving into more disordered configurations. Gravity pulled matter together to form clumpy galaxies and stars, which seems like an increase in order. But the process of star formation releases enormous amounts of heat and radiation, vastly increasing the overall entropy of the cosmos. This low entropy beginning is perhaps the most profound initial condition of our universe. It provides the thermodynamic gradient that powers stars, drives geological processes on planets, and ultimately fuels life itself. The energy of the Big Bang wasn't just raw power, it was organized power. The question then becomes, why did the universe start in such an improbable, low-entropy state? We don't have a definitive answer, but it's a crucial piece of the puzzle. The arrow of time that governs our lives is a direct inheritance from the first moments of the cosmos. Section 7. Beyond the Bang. A multiverse of possibilities. It is not the only idea. Science thrives on exploring alternatives. Some physicists think the Big Bang might not be unique, but one event in an eternal, larger-scale process. Cyclic universe, infinite cycles of expansion and contraction. Expansion slows and collapses into a big crunch, then rebounds into a new Big Bang. Multiverse. Eternal inflation makes our universe one bubble among many. Quantum fluctuations spawn new bubble universes. Each bubble may have its own laws and constants. Our universe is simply the one we inhabit. This explains fine-tuning for life. With infinite universes, some will have the right properties. Our universe as a three-dimensional brain in higher dimensional space. The Big Bang caused by a brain collision. The collision released massive energy, heating and triggering expansion. Brain collisions could repeat like cycles. These speculative models push imagination and scientific creativity. The energy paradox is not a dead end. It has produced some of the most profound ideas in science. Zero-energy universe concept. Positive matter energy balanced by negative gravitational energy. Initial heat came from density, and the arrow of time stems from a low-entropy birth. The question shifts. Where did the energy come from? To why do the laws of physics permit a universe like ours? That question drives our quest and reminds us the cosmos is stranger than we imagine. The Big Bang was not an event in the universe. It was the event that created the universe.